Hello everybody. Today I am going to start a new topic as part of this lecture series on NDT, and this will be on acoustic emission testing. Which is also known as A testing in short. Okay. So, like what you always do, first we will learn about the basic principle of this technique, and then we will see how it is done. In the last topic, if you remember, it was on ultrasonic testing, and what we saw in that case is that you have a piezoelectric ultrasonic transducer through which you are sending ultrasonic waves into a sample, and whenever these sound waves reflect back from a surface or from discontinuities, we collect this echo and then we display them. Okay. And that is how we get to know about the presence of defects in a given sample. Okay. So, utilizing sound waves and their reflection, we do the NDT in that case. In this particular technique also, acoustic emission testing, as the name suggests, particularly the term acoustic, it also indicates that it has to do something with sound waves. Okay. But in this case, it is bit different from what we do in ultrasonic testing, in the sense in ultrasonic testing you have a two-way traffic. You first send the sound waves into the sample and then you collect the echoes back. Okay. So, when you send sound waves inside the sample, as we would have discussed, these sound waves propagate by creating oscillatory movement in the atoms or in the molecules. Okay. So, it propagates by some kind of elastic waves through the sample. Okay. Now, for any reason, if you have this kind of waves generated inside the sample itself, okay, then when they come out from the part, and if you could receive them by a sensor, then also that could be used to do non-destructive testing. Okay. But in order to create these elastic waves inside the sample without exciting it, there has to be some movement which can provide this oscillatory movement to the atoms. Okay. And for that to happen, the sample has to be loaded, then only you could have some dynamic events inside the sample, which will in turn create some kind of elastic stress waves, which will propagate through the sample and come out. Okay. So, if you have a dynamic or moving defect when the sample is loaded, then in this case also some kind of sound wave or some elastic wave can be generated inside the sample and they will come out of the sample. Okay. So, if you have a sensor, you could receive this elastic waves, which are known as acoustic emission waves. Okay. So, the source of acoustic emission wave is the redistribution of a stress field inside the sample due to movement of some kind of defect. For example, it could be a crack which can initiate and then propagate. So, due to that crack propagation, there will be some movement on an atomic scale, and due to that these elastic waves will be generated, and if you have a sensor to receive them, you would be able to know that there is a source of acoustic emission inside the sample, and hence there could be some defect which is active. Okay. But in order to generate those elastic waves, okay, the first requirement is that the component or the part which is being examined must be loaded, because in order to create that stress wave, you need to apply some load, then only there will be some change like crack initiation or propagation, which can generate these elastic waves. Okay. So, that is the first requirement, that the part or the system which is being examined must be loaded. Okay. So, let us say you have a component and you load it in a particular fashion. Then in some part of the sample, this stress waves will be generated. So, that will be the source of the emissions, and then these waves will propagate from this source. Okay. So, this is a source of acoustic emission or stress waves generated due to this applied load for whatever reasons, which we are going to talk about little later. Now, if you have sensor over here which can sense these waves coming out from the sample, then you would be able to collect them. So, first thing that you need to do in order to collect and then utilize them is to amplify them, because generally the intensity of this kind of emission will be very low. So, you use a pre-amplifier and then send this signal to the detection and the measurement system, which will generate an electrical signal out of these elastic waves and give you something to see on the display. Okay. And then that can be interpreted, and then you would be able to know if there are any defects which are active inside the component. Okay. Right. So, this is how this technique works. So, the first requirement is that it has to be loaded. If there is no load, then there is no emission. So, this is the first characteristic feature of acoustic emission. If the defects or the damage that you have inside a component, if it is not active, okay, then you are not going to get any emission out of it. Okay. So, that is the first and the foremost difference between acoustic emission testing and any other NDT method, in which case we have seen that we detect the existing defects, okay, whatever it may be, which may or may not be active. For example, if you have a crack, that crack may not have to be propagating in order to be detected by other NDT methods. Okay. But in this case, if you want to detect that crack, it has to be active and it has to propagate. Okay. So, that is the prime difference between acoustic emission testing and any other NDT technique. Okay. And for the defect and the cracks to be active, the part has to be loaded. Okay. So, that is how this particular characteristic come into picture, that if there is no load, there is no emission. Okay. So, when you do acoustic emission testing, then the part has to be loaded by controlled loading. So, this can be before service or during the service of that particular component. And if it is a load bearing structure, then you know it is anyway loaded. Okay. So, all you have to do, you have to place the sensors at appropriate locations and then try and see if you get any acoustic emission signal coming out from different regions. Okay. So, this kind of system will be loaded anyway. So, then in these cases there is no need to load it externally. Okay. And the other important aspect of this particular technique is you would be able to inspect a big structure in a single inspection. So, you do not really have to do local examinations in this case like you do for many other NET techniques. So, even if you have a very big structure or very big area to be inspected, that can be done in a single examination itself by placing a number of sensors at different locations, where you think there could be a potential source of damage, which could lead to acoustic emission events. Okay. So, this is another characteristic feature of this particular technique, that you do not need to do inspection in small local areas, rather you can inspect the whole structure in one go itself, and that is how this offers some advantage in terms of time and cost. Okay. So, if you see the sources of acoustic emission, as I said, you need a stress field which will generate these stress waves, which will propagate through the sample and will be received by the sensor. Okay. So, when you load a material or a system, then various things can happen depending on what kind of material or what kind of system it is, which can act as sources of acoustic emissions, okay, by providing you some active defect, okay, inside the component. For example, if you have a metal, so in metallic systems, when it is loaded, different phenomena can take place. For example, you could have micro and macro cracks initiating and propagating. So, initiation and propagation of cracks when a metallic system is loaded can generate lot of acoustic emissions, lot of these stress waves, and this will serve as a source. Okay. Then you could have some micro dynamical events like twinning, when you talk about metals, metals deform mainly by two mechanisms. One is known as slip and the other one is known as twinning. Okay. whenever a metal is loaded, you could either have slip happening or twinning happening depending on the conditions, and that is how they plastically deform. And the process of slip happens due to a lattice defect, which is known as dislocation. So, when you load a metallic system, these dislocations will move, and due to that movement it creates what is called a slip, which is movement of atomic planes over one another as if they are slipping over each other when the dislocations move. Okay. So, movement of these lattice defects known as dislocations can also generate acoustic emission inside metals. Then if there are brittle inclusions or some kind of impurity which is leading to formation of this kind of brittle foreign elements or foreign inclusions inside a metal, then fracture of this kind of brittle inclusions when you apply the load can also generate acoustic emission. Then other events like a chemical action such as corrosion which is common in metals can also lead to these elastic stress waves or acoustic emissions. Okay. Then many of the metallic system goes through what is known as phase transformation, wherein it changes from one phase to another phase at a particular temperature for a given system. Okay. So, the parent phase and the phase which is forming they are different and their volume also could be different. So, due to this change in the volume it can lead to stresses inside the material, and due to that stress again this kind of acoustic emission can be generated. Okay. So, phase transformation can also be a source of acoustic emissions in metals. So, this happens as I told due to a change in the volume. Which leads to small strain effects. Okay. And then this in turn will generate the elastic waves or the acoustic emissions. Then if you take a material like a composite, then in that case acoustic emissions can generate due to fracture of the reinforcing fibers at medium strain level. Delamination, this is again a type of damage in composite materials which can happen at high strain levels. Then another common phenomena in composite material when it is loaded is fiber pull out. These fibers will simply pull out from the matrix, leaving behind some voids. So, that kind of event can also generate these stress waves and will lead to acoustic emission. Then the matrix also can crack. So, matrix cracking and fiber debonding from the matrix. This can happen at low strain level. In the other previous two cases, it was at medium strain at high strain, and at lower strain you could have this kind of phenomena happening inside a composite material. The matrix can crack, or the fiber can separate, or the fiber can debond at low strain levels. Okay. So, these are the different sources in case of composite materials. Then if you have a system like a concrete, there also you have those reinforcing bars which reinforce the concrete. Okay. So, those reinforcing steel bars we all have seen. So, they are bonded to the rest of the material, the rest of the concrete material. So, then there also when it is loaded, different kind of phenomena can happen which can lead to generation of these stress waves or acoustic emissions. For example, there also it can crack. So, you can have micro and macro cracks. Then the reinforcing bars can separate. And when there is some separation, there could be also mechanical rubbing between the separated parts, which can also lead to generation of these acoustic emissions. Then in a component like a tanker which carries a huge volume of liquid or gas, okay, there could be some fluid leakage in cases of big tanks which store or carry fluids, and due to that you could have this flow past the leakage or the opening, and this can generate lot of elastic stress waves. That means, this can also serve as a source for acoustic emissions. Then turbulence or the turbulent jet. Due to the presence of a liquid head or some fluid pressure. if there is any turbulence in this liquid or there is any turbulent jet, that will also create a lot of stress which can lead to acoustic emissions. And in this kind of component material erosion is a common phenomena. So, there again it will generate lot of stress leading to emissions. Okay. So, these are different kind of sources depending on what kind of component or what kind of system you have. Okay. So, we have understood something about these acoustic emissions now, what their sources are, how they generate inside a component. Okay. And what is the difference between this acoustic emission testing and any other NDT technique, that also we have understood. Okay. So, now before we conclude today, let us see the typical features of this kind of waves. I have talked about a bit in the beginning, but let us list them down. So, this is what we have learned so far. Sources of acoustic emission is the elastic stress field or the elastic stress waves, which happens when the component is loaded. So, let me reiterate this again: no load, no emission. This is the typical characteristic of acoustic emission. Then acoustic emission testing does not need any external source. It does not need any external supply of energy. All you do, you listen to the waves which come out from the sample. So, instead it listens to the waves coming out of the part. And this also we have talked about, only active features are highlighted, unlike the other NDT methods which detects existing defects which may or may not be active. So, in this case this acoustic emission testing, it detects the movement of defects. Okay. So, that is why only active defects are highlighted in this case. The entire structure can be inspected in a single examination, as I would have said before also. and that is how this can save time and cost. And this is primarily qualitative. This does not really provide you any idea about the size of the defect or the location as such. So, this is primarily a qualitative method. Okay. So, these are the typical characteristics of acoustic emission. So, in this class today we have learned about the basic principle of this particular technique, and we also saw the sources of acoustic emission. In the next class we are going to continue on this, and then we will see how the test is done, what are the test parameters and the other aspects. Okay. So, for today I will stop here. I will see you next time. Thank you.